Okay, so we are doing examples 2, 3, 4, and 5 from the related rates lesson 4. So a pebble is dropped into a calm pond, causing ripples to form in concentric circles. Okay, so we got a pond and we got ripples forming. Ignore my not so circular ripples. That's okay. So the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. That's happening to the radius. So we're going to say dr dt is a positive 1 foot per second. Okay. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So the area of the ripple, what is happening? So we want dA dt when r equals 4. And we know that if we're finding dA dt, we're probably going to want an area formula. These are circles, so I know A is pi r squared. Okay, so I'm going to start with my A is pi r squared. So then my dA dt is 2 pi r dr dt. So then if I want dA dt when r equals 4, then I have 2 pi times 4 times dr dt, which is 1. So my dA dt is 8 pi, okay, and that's a rate, and so it's the rate that the area is changing. So the area would be in feet squared per second for dA dt. So the area of the ripples is changing by 8 pi feet squared per second. All right, let's look at the next one. So air is being pumped into a spherical balloon, okay, at a rate of 800 cubic centimeters per minute. So air is going in, and that would be changing the volume of the balloon. So you're actually given dV dt, because as the air gets pumped in, that is how the volume is changing. And so that's a positive 800 centimeters cubed per minute. You want to know how fast the radius is changing. So you want to know dr dt, and you want to know that at the instant when the radius is 30 centimeters, so when r is 30. Okay. For a sphere, we're going to need the volume formula, and that's 4/3 pi r cubed. Okay. So we're going to start with that. V is 4/3 pi r cubed. So then dV dt is going to be 4 pi r squared dr dt. Well, you know your dV dt is a constant 800, so we can put in 800. And then we have 4 pi. Well, we want the instant when r is 30, so we're going to plug in r for 30 dr dt. So that's going to lead us to our dr dt when r is 30 will be 800 over 4 pi times 30 squared, so that's 900. So I know here I can cancel out the 2's, cancel out the 0's. So then your dr dt when the radius is 30 will be 2 over 9 pi. And then check our units. The radius is changing. The radius is just a distance, so it'll just be in centimeters per, and our time, which is minutes. So the radius is changing at 2 over 9 pi centimeters per minute when the radius is 30 centimeters. Okay. So that's an instantaneous rate of change, which is why we need the instant when the radius is 30. All right, let's move on to example 4. So the top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. Okay, so I'm going to pause there. We know the ladder is 25 feet, so I'm going to draw a wall, okay, and then we're going to have our ladder that's sliding down it. So here's kind of a ladder. I know that we can relate here. If this is A, we'll say this is B, this is C, because we're making a right triangle. So our formula is probably going to be A squared plus B squared equals C squared. I know that the C is always going to be a constant 25 because the height of the ladder won't be changing. Okay. So I'll write that as part of our given. Our dc dt is 0 because it's just a ladder. The ladder's not going to change. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom and the wall? So for us, that's our B. Okay, so we're looking for how this distance is changing. So we're going to find dB dt when the ladder is 7 feet from the ground. So that would be when our A is 7. Okay. We also know we didn't use the constant rate of 3 feet per minute. It's sliding down. So that's our dA that's changing, and it's decreasing. So it's -3. So let's take our A squared plus B squared equals C squared. So we have 2A dA dt plus 2B dB dt equals 2C dC dt. Okay, so now we got to plug in. So we have 2, okay, well our A is 7 and our dA dt is -3 plus 2. Ooh, and we don't know our B, so we're actually going to pause. We got to find our B before we go on. So we know A squared plus B squared equals C squared. So if our A is 7, I have 7 squared plus my unknown B squared and my 25 squared for C. So if you solve that, you end up getting that B is going to be a 24. For the sake of the length of the video, I'm sure you can calculate that out, but your B will be a 24. You also might know that 7, 24, 25 is a perfect right triangle whenever you're Pythagorean triples. So we get 24, and our unknown dB dt will be 2 times 25 times our dC dt, 0. So then we're going to get -6, so we get a -42 plus 48 dB dt equals 0. So your dB dt, when your A is 7, will be 42 over 48, which simplifies to 7 over 8. Okay? And it's a distance changing, so it'll just be in feet. And our time, minutes. So feet per minutes will be your answer. So when the ladder has already slid to 7 feet down on the wall, then the distance that the bottom distance, our B, is changing is 7/8 feet per minute. All right, our last one's a little tricky. And then in class, I think we will do 6, 7, and 8 on Monday. So at noon, a ship is 150 kilometers east of ship B. So we got ship A, and it's going this way. We got ship B, and it's going this way. And then we got a C connecting them. So we know that we can use A squared plus B squared, and it'll be C squared. Okay. We're given that ship A's distance is changing by 35 kilometers per hour, and ship's B distance is changing by 25 kilometers per hour. We still want to find dC dt when t is 4. Okay. So we know also that they started 150 kilometers apart. So we're going to use that later. So if we just do our A squared plus B squared equals C squared, okay, we get our 2A dA dt plus 2B dB dt, and it'll be 2C dC dt. Okay. So our problem before was the funkiness with A, right? So our A will be A's distance, this distance here. So we just have to think about it as A's distance really is 150 minus, it's been traveling now at 35 kilometers per hour for 4 hours. So A's distance is a 10. Okay. B's distance is the same as before, 25 times 4, which is 100. C's distance is still going to be that square root of 1,100 because we're going to do A squared plus B squared equals C squared. Okay. So then we get 2 times 10 times here, the 35. But if we think about this distance as being A, is that distance increasing or is that distance decreasing? That distance right now is decreasing. So when you go back to your dA dt, think of it as a negative. That is why it's a negative. Plus 2 times b, well, our b is 100, dB dt, which is our 25, equals 2 times our c, dc dt. So now we should get, let's see, 2, I am using the calculator, times negative 25 plus 200 times 25, 4,500 equals 2 square root 100 dc dt. So your dc dt, that distance between the ships after 4 hours, is changing by a rate of 4,500 over 2 square root 10,100. And your units on that, okay, and since I broke out the calculator already, we might as well finish it since it looks nicer as like a number. 22.388. And that's a distance, so kilometers, and it's changing per hour. Much better that second time around. I'm sorry I butchered the first attempt at this problem. My bad. But we should be better now in class for examples 6, 7, and 8.